Hello everyone, in this video, we are going to present our paper, Walk in the Cloud, Learning Curves for Point Clouds Shape Analysis. In the first part of this video, we demonstrate an overview of the proposed approach and discuss why existing methods cannot suffice, and hence our method is desired. Then, we present formal definitions of the proposed terminologies and brief workflows of our algorithms. Finally, we wrap it up by demonstrating the superiority of our method on 3 fundamental tasks with further analysis. 3D vision tasks are one of the most active tasks in the computer vision community. In the recent years, many efforts have been made for analyzing all kinds of 3D visual signals, especially point clouds. Differing from conventional 2D vision tasks, point clouds are usually in irregular and unordered forms. Hence, the effective designs of feature aggregation and message passing schemes among point clouds still remains challenging. Existing feature aggregation operators could be roughly classified into 3 categories. In this paper, we proposed a new paradigm for point cloud feature aggregation, namely curve aggregation, that first groups a continuous set of connected points to form a curve, and then aggregate the grouped curve features back to each point. But why existing local feature extractors cannot capture good geometric patterns? Let us first have a close look at the local aggregation paradigm. Although such formulation is intuitive and efficient, we argue that seeing only locally located points can't model good object geometric traits, which require relation modeling in a longer range. Let us consider a simple 2D point cloud plane as an example. Point A, B, C are 3 key points, and the blue points are their KNN neighbors. Obviously, point A and B will have almost identical encodings if using local aggregations. Only the points that are in extreme geometric positions, such as point C, are able to encode different features. Given such observations, we claim that local feature aggregation-based neural networks are likely to have very similar point features, especially at shallow layers. Here we visualize feature maps of a chair object extracted by DGCNN, and found that the chairs, back, and seat indeed have very closed features, regardless of pooling scheme. So, what is a curve exactly? Generally speaking, a curve is an ordered connection of adjacent points that can be grouped through a given walk policy. Consider the previous example again. A possible curve could span over all point A, B and C that carries much longer range information. We now present the strategy to group curves in the semantic space of any given point clouds. Here are the 4 parameters and functions that need to be defined in advance, before we can articulate the naive curve grouping process. However, there are several major flaws in the naive working flow. Consider that for any deterministic walk policy, when the input signals are fixed, the output will always be the same. Such that, in its current form, if we visit a same node multiple times, the walk policy will always transit to the same point. This causes loops that carry repeated and very limited information for each curve, and therefore should be avoided. To achieve this, we consider not only the point features itself during the walk but also a curve descriptor that encodes the overall curve progress. In our experiments, we used a simple dynamic momentum paradigm to encode the curve progress. After the grouping completes, our proposed curve aggregation module then maps the grouped curves back to enrich all point features with the encoded geometric information. We then embed our curve grouping module and curve aggregation module into a simple ResNet style network, referred to as CurveNet. The network architecture is outlined as below, and more details can be also found in our main paper and supplementary material. Our proposed method was benchmarked on 3 most fundamental point cloud shape analysis tasks. Our CurveNet achieves state-of-the-art results on all 3 tasks, with and without using the voting strategy. Finally, here comes our conclusion. In this paper, we proposed a novel feature aggregation paradigm for point cloud shape analysis. Curves are grouped and aggregated for better depiction of point cloud object geometries. We studied potential drawbacks during curve grouping and provide solutions to avoid loops and suppress crossovers. Our CurveNet achieves state-of-the-art results on 3 fundamental point cloud object analysis tasks.